A metal rod with a length of 22 centimeters lies in the XY plane. It makes an angle of 35.5 degrees with the positive x-axis and an angle of 54.5 with the y-axis. All right. So do these add up to 90? It's yes, I think they do. So 50 plus 30 is 80, and the rest of that adds up to 10. So yes, 90. So I don't think they had to give us both angles. With the positive y-axis, the rod is moving in the positive x direction with a speed of 6.8 meters per second. The rod is in a uniform magnetic field, and it gives us this crazy magnetic field. So first thing we're going to do is draw everything out. So I'm going to draw my XYZ plane. So we have to be careful about how we draw the XYZ coordinates because it's not a. We had to make sure it's a right-handed. You can't just randomly throw down X's and Y's. So this is just the way I have memorized for XYZ coordinates. But this emphasizes more the Z plane because it's up and down. So what I'm going to do is I'm going to rotate it towards us so that we have X going this direction, Y going this direction, and then I'm going to draw the Z direction like this, where the Z is coming straight at. I kind of offset it a little bit, but the idea is that towards us is Z. So these are the same idea. And they tell us that we have a rod, XY, and let's do blue, do 54.5. So we have a rod kind of like this, where this angle right here is 54.5 degrees. A metal rod length lies in the XY plane, makes an angle with a positive and an angle with a positive. The rod is moving. Yep. And I'm going to say it starts at the origin. Can I do that? Can I just move this? Oh, I'm going to say it like that. Yep. I think I can totally do that. So 54.5. Nope, that's the first one is 35.5. Whoop. The conceptual part doesn't matter. So we have 35.5 right there. All right. So I think we're good. With positive y-axis, the rod is moving in the positive x direction with a specific speed of 6.8. So it's going to be moving whoop, this direction at 6.8 meters per second. All right, got that. And then we have a magnetic field that's positive x, negative y, and negative z. So it's the magnetic field is going to be kind of crazy. I'm going to draw it, I don't know, sort of like that with some crazy perspective going on. So it looks like the magnetic field in the XY plane. It is not in the XY plane because it's also in the Z plane, but it's going back into the board. So we need to keep that in mind and not get too attached to that picture. All right, the rod is this, blah, blah. Okay, what's the magnitude of the EMF, the induced magnetic force, which is the same as voltage induced in the rod. Okay, so to go back on some concepts here, I'm going to draw another picture. Just to go with the concepts. So we have a rod like this moving this direction, and this is the idea of generator action. Let's say we have a magnetic field. What color did I use for magnetic field? Blue or green? We'll do green. Green. Let's say a magnetic field going into the board. And so what happens is we're going to have a force. So whenever we have, it's called the Lorentz force. And when I think of forces on a charged particle, I think force equals QE plus QV cross B. And there's no electric field here. No one said anything about electric fields. There are electric fields, but for all intents and purposes for what we care about, they're not going to be contributing in here because it's not mentioned. I just write it out here because this is kind of an all-encompassing formula. So now what we have is a force on charges. In this case, we're going to they're going to be electrons, but we're going to say they're in a metal, in a conductor, the charge carriers are negatively charged electrons. I'm going to say that they're positively charged just so I get the signs correct. The same having an excess of electrons is the same as having a deficit of protons. So the idea is you can look at it either way. It's just the way science, physics has decided to go. I'm going to say Q is positive, V is to the right, and B is into the board. So we're going to do the right-hand rule to find the direction of this force. So V is to the right. V cross B into the board is going to give us up. And so V cross B is going to be V cross B is up. Yep. And so this is going to be direction of up. So what this does is this is effectively causing a force pulling the positive charges up, which means you're going to have a lack of positive charges on the bottom, which is the same as a negative. You have a separation of charges. You can think of this as like a parallel plate capacitor. We have, that's terrible line. Not that terrible, just not as good as I would like. There we go. Positive up here, negative down here. You have the same concept. So parallel plates, which is kind of like, parallel plate capacitor, voltage. This should all intuitively be like, okay, that's similar, I guess, maybe, sort of. And so that's the concept that's happening here. Now, the issue is this bar isn't perfectly aligned like this. I basically ignored how this cross product worked because they were perpendicular. A lot of times you'll see cross product as VB sine of theta, because cross product is a sine of theta because it's a cross product is a measure of how perpendicular two vectors are. But theta is the angle between the two vectors. So, but we got some crazy numbers here, and we have no idea what the angle is between those. So we're going to have to go a little bit more in depth. So the formula we're going to have for the voltage across a bar moving in a magnetic field is going to be electromotive force, which is voltage, is LVB. Now, that might feel kind of random, and there's some math behind it. And this isn't by any means a derivation, just kind of feels that maybe it's correct. So if we have force equals QVB, it's QV cross B, but I'm going to assume that things are perpendicular. Force is the same as Q times E, and E, voltage equals negative electric field dL or dx. And so the idea being that, like, if you have a parallel plate capacitor, electric field is going to be voltage divided by L, uniform electric field. So QV over, I'll say L, equals QVB. And this is kind of sort of how there's a relation. This is a voltage, and that's magnetic field. Voltage equals LVB. So that's the idea of E equals LVB. So to be, and then the mnemonic I use for that, that I learned for that, is everybody loves velvet bunnies. Now to be a little bit more formal, make sure no vector there, just to show that it's velocity, not voltage. We're actually going to use the formula. Electromotive force, which is the same as voltage, is integral V cross B dot dL. Now for this, V and B are both constant. So if we look up here, the velocity is 6.8 meters per second to the right. Magnetic field, they give us as a uniform magnetic field. That's also a constant. So V cross B is going to be a vector. So it's going to be another vector, v cross b, and that's going to be dot product cross times dl. So this is going to be v cross b. So we basically can pull this out of the integral, v cross b dot l. And so this becomes a bit challenging because it's like, all right, now we need to find a cross product between v and b and then dot that by the l. A little bit difficult, but we can totally do this. So we're going to go back, we're going to take this formula because this is what we want. This is what we're going to, I'll put a little epsilon here for EMF equals, just so I remember. Bring this up here, and now we're going to keep going on with our derivation here. So v, we need to see what v is. So v, I'm going to say, we need to write this in terms of a vector. So I'm going to write it in terms of, so we know it's 6.8 meters per second to the right. So I'm going to say this is 6.8 comma 0 comma 0 vector. I'm going to say the magnetic field is 1.6 negative 2.4, 1.6 comma negative 2.4 comma negative 0.09. Negative 0.09. And this is another vector. So first thing we need to do is we need to do the cross product of these. So the way we're going to do that is we're going to write up a matrix. So I'm going to say I, J, K, 6.8, and the order of these two matter. You can't, if you switch up the V and the B, then you're going to get the negative answer, which we're looking for the magnitude, so it doesn't actually matter, but I still want to keep things correct if I can. So that's supposed to be 2.4, negative 0.9. So let's see if that's correct. 1.6, negative 2.4, 1.16, negative 0.24. All sorts of mistakes here. So we're going to do, can I just grab that little, yes. Yes. And then 0.09. Alright, so let's check this again. 0.09, 0.24, 0.16, negative. Okay. So, yep. Move that point over there. Move that over there. Got it. Now we're going to do the determinant. So this is how we do the cross product of two vectors. This is the velocity. This is the magnetic field. And so we're going to get, start with the I. So we're going to do I times 0 times negative 0.09 minus 0, this will be a 0, 0 times negative 0.24. Then we're going to switch the signs, so negative j, 6.8 times negative 0.09 minus, now we're going to do, let's see, we did that times that, now we're going to do 0 times 0.16. And then we're going to switch the signs again, which gives us back to a positive k. So we're going to have 6.8. Oh, this is supposed to be positive k. Actually, I'm struggled. There we go. Perfect. Go team. So now we do 6.8 times negative 0.09 minus, no, not 0.09. Fail. So we're doing k, so it's going to be 6.8 times negative 0.24. There we go. Minus 0 times 0.16. Yep, that seems reasonable. Now I'm going to go through this and get rid of the zeros. So 0, 0, 0, and 0. And we are left with, so I'm going to cancel the negatives there, j times 6.8 times 0.09 plus minus, because we have a negative sign right there, K 6.8 times 0.24. Now, is this supposed to be 6.8? It is supposed to be 6.8 because it's moving at 6.8 meters per second. Yep, 6.8 meters per second. All right, we got that part. Come back on over here and write this out. We'll do a calculator. Oop. On clear, 6.8 times 0.09. And it's going to be, so this vector is going to be 0 because there's no I. It's going to be 0.612. And then for K, we're going to have 6.8 times 0.24. That gives us 1.632. Negative 1.632. And this is the cross product of the velocity and the magnetic field. Okay, so now that we got that part of the equation done, so this is our end goal up here. So we found this part. So now we need to do a dot product of that with the L, the length. So the length here, they tell us, is 22 centimeters, and they give us an angle right here. So we can totally do that. I'm going to actually just copy and paste this down over here and then find it. So this L, this length, is basically going to be a triangle, where this triangle and this angle is going to be 35.5 degrees. I should probably check that real quick just to make sure I'm not too crazy. 35.5 with the positive x-axis. Yep. So 35.5. So we got our triangle here. 35.5 degrees. This is 22 centimeters, which I'm going to write as 0.22 meters. And now we're going to do, let's see, 0.22 times, we'll do the sine. Oh, wait a second, make sure I'm in the correct mode. Degrees, yep. Sine of 35.5 degrees. And that should give us, yep, about half. 0.128. 0.128 meters. Now I'm going to do the exact same thing, except it's going to be cosine 35.5. That seems reasonable. And it's going to be 0.179. 0.179. So now I can write this as a vector. L is going to be x value of 0.179 and y value of 0.128 and a z value of 0 because it's just in the xy plane. Alright, so now we can do our dot product. So we have our, leave it like that. We have our V cross B and we have our L. Now we can do V cross B dot L. So we're going to do V cross B dot L, which is going to be 0, 0.612. I'm glad there's a lot of zeros. Negative 1.632. Vector symbol. Dot. 0.179. 0.128. And thankfully, dot products tend to be a little bit easier to do than cross products, at least from a math point of view. So I know this is a very math and heavy question, not as intuitive as I like, but such is life sometimes. So now dot product, we're going to do 0 times 0.179. So 0 times 0.179. Then I'll do, let's do light green, plus 0.612 times 0.128, which is nice because that's not going to be a 0. plus negative 1.632 times, get rid of that, 0. Yep, I'm good with that. Ooh. So that goes to 0. That goes to 0. Okay, I'm going to put a little arrow right there too. And we're just left with this as an answer. And so, let's do some calculator. 0.612 times 0.128. 0.612, 0.128. And we get epsilon equals 0.078. 0.07. Oh, I can do a better job of that. 0.78 volts. So the idea here, I'm going to backtrack because this was a crazy amount of math. So we had our problem up here. Metal rod of a length moving in the magnetic field. So metal rod moving through a field. The idea with that is you have the Lorentz force, which is basically forcing the charge carriers, i.e. electrons, to one side of the bar, which is also causing an absence of said charge carriers, i.e. electrons, on the other side of the bar. When you have a non-uniform distribution of charges here, this is basically going to be similar to what I used was a parallel plate capacitor. Not that extreme, but same concept. This difference of charges is going to create a voltage, a gradient. And the formula for that is epsilon equals LVB, but that's when everything is perpendicular and working nicely. When it's not as nice, we're going to have to use the concept of epsilon, which is electromotive force, is the integral of V cross B dot dl. So since we have a constant velocity, we have a constant magnetic field, we can pull them out of the integral. The integral of dl just becomes L. And so we have V cross B. Yes, and this dot product is also constant because it's a straight line. So V cross B dot L. So we're like, all right, how do we do V cross B? Well, velocity, we just write it as a vector. Magnetic field, they basically give it to us as a vector. We put it into a matrix, find the determinant of it, and that's just the methodology of doing the cross product of two vectors. We get the cross product, which down here, and we take that cross product and we do the dot product, and bam, we get a final answer of 0.078 volts. So, relatively simple problem that's presented to us in a very complicated way. So, hope this made sense. I know it was more math, less intuitive, but this is a good problem to be able to kind of approach. As long as you don't panic and just kind of work your way through and know the right formulas, it's not too bad. But it is cumbersome and prone to mistake, human performance traps. Hope that helped. See you next time.